The first of the additional equilibria that we will look at are buffers. Now, a buffer is going to be a mixture of a weak acid and its conjugate base, or a weak base and its conjugate acid, and that mixture will resist pH change when small amounts of a strong acid or a strong base are added. We'll do some calculations with that in a few minutes. Now, the most common equilibrium that is used in a college chemistry course is a solution of acetic acid and sodium acetate. A lot of the lab kits that we use this type of a buffer in order to show you how buffers act and react. I don't know if your lab kit will use this buffer. Our lab kits are dynamic. So what we have here is this picture. On the left, we have two solutions. They're both at a pH of 8. There's an unbuffered solution on the left and a buffered solution on the right. And I'm looking at the two yellow solutions in the left-hand picture. In the right-hand picture, a little bit of hydrochloric acid was added to each of the beakers. The unbuffered solution, the color changed to the acidic color, the red, whereas the buffer solution maintained its pH. It stayed yellow. So how that works is we have an equilibrium. So we have our weak acid and water. These are aqueous equilibria. Our weak acid and water, and that's going to react to form the hydronium ion, or our acidic water, and the conjugate base, or the acetate in this particular example. Now the pH is only going to change a little because this is an equilibrium. So when we add something like a little bit of a strong acid, that's going to increase our acidic water over here on the right-hand side and shift that equilibrium to the left and rebalance that equilibrium. Now, when we're talking about calculations, we have this particular example, pH changes in a buffered and an unbuffered solution. So, for example, part A, calculate the pH of an acetate buffer that is a mixture of 0.1 molar acetic acid and 0.1 molar of sodium acetate. So if we come over here and we're going to have our weak acid, we're going to have our acidic water or our hydrogen ion, and we're going to have our conjugate base. Initially, we have 0.1 molar, or that's the concentration of our weak acid, and we also have that as our concentration of our conjugate base. We're going to change that in order to form the equilibrium because currently we have none of this hydrogen ion and we need to balance this equilibrium. So we will shift it by some value x. And we don't know what that x is, but we will calculate it. Then at equilibrium, that's going to be 0.1 minus x. The hydrogen ion concentration will be x. And the anion, the acetate in this case, will be 0.1 plus x. Now the Ka here is 1.8 times 10 to the negative 5. And if it wasn't given in the question, it should be. You can always look it up. There are several tables available. So this Ka value is going to be equal to the product of the products. So x, 0.1 plus x, divided by the reactants, 0.1 minus x. Now here we have a situation where we can reduce or simplify this expression. This being 0.1 and our Ka being 10 to the negative 5, we're right on the cusp of whether we can or cannot. But in this case, we can. So we're going to simplify this expression. 1.8 times 10 to the negative 5 is going to be equal to 0.1x over 0.1. So our 0.1x will be 1.8 times 10 to the negative 5. Now that the units here are molarity, capital M, and that is the concentration of the hydrogen ion. Going back to the original question, they want the pH. So the pH of this value, remember pH equals the negative log log of the concentration of the hydrogen ion. So in this case, we're going to take the negative log of 1.8 times 10 to the negative 5. We have the log 1.8, I need to use the exponents. So it's second, and the comma gives me the E. Then I use -5. So the pH is the negative of that value, so the pH is going to be equal to 4.74. So that's A. Calculate the pH after 1 milliliter of 0.1 molar NaOH is added to 100 milliliters of the buffer, giving a solution with a volume of 101 milliliters. We need to start with approximately our equilibrium concentrations. Now, because 0.1 minus 1.8 times 10 to the minus 5 is going to be approximately 0.1, that's where we're going to start. And what we need is our weak acid and conjugate base. Now we're going to add a strong base to it. We're going to add 1 milliliter, so 0.001 liters of a 0.1 mole per liter sodium hydroxide solution. So that's going to give me the number of moles of base that we're using. Now the number of moles of base that we're using needs to be compav. Because we've been told that we have 100 milliliters of this, and this is a capital M molar, we need to convert these into moles. So 0.1 moles per liter times 100 milliliters, or 0.100 liters, is going to give me my moles. So here I'm going to have 0.01 moles of my acid, and I will have 0.01 moles of my conjugate base. Now when I add my strong base, I'm going to remove some of this weak acid. When I remove from the weak acid side, I'm actually adding to the acetate side. So I have 9.9 times 10 to the negative 3 moles of my weak acid left, and 0.0101 moles of my acetate left. Now I need to convert that into molarity. So I need to divide this by my total volume. So now the total volume of my mixture is 101 milliliters. So if I divide these moles by 0.101 liters, and these moles as well, I will get the new concentration. So my new concentration, so my capital M molar, and this is going to be my initial for the new equilibrium, is 0.098 capital M molar. And this is my weak acid. And for my acetate, it's going to be 0.1 capital M molar. Now initially, I'm having effectively 0 hydrogen ion concentration. So now I'm going to change, and I'm going to change by removing some of the weak acid, adding to this side, adding to the product side as it's written. So at equilibrium, and now I can calculate the new equilibrium. Now this is right on the cusp of being able to simplify or not. I'm going to simplify in this case. So I have 1.8 times 10 to the negative 5 equal to 0.1 over 0.098x. X is equal to 1.76 times 10 to the negative 5. Now that's my hydrogen ion concentration, but the question wanted the pH. Is the negative log of the hydrogen ion concentration. So in the calculator, I'm going to take the log. and get a pH equal to 4.75 for part B. Part C, for comparison, we're going to calculate the pH after 1 milliliter of a 0.1 molar sodium hydroxide solution is added to 100 milliliters of a solution of an unbuffered solution with a pH of 4.74. So this is going to be a 1.8 times 10 to the negative 5 molar solution of HCl. So what we're going to start with now is our HCl, and this is part C. HCl reacts to form our hydrogen ion and chlorine anion. Now the initial pH of 4.74 means our initial hydrogen ion concentration is 1.8 times 10 to the negative 5th. Remember that pH equals the negative log of the hydrogen ion concentration, but when you're given the pH, you can take the inverse log or the anti-log in order to find that hydrogen ion concentration. On this calculator, it's second and then log, that's the inverse log function, and then the negative sign, 4.74, and you get a 1.8. In this case, it looks like a 1.82 times 10 to the negative 5th, but 1.8 works just fine. So that's what we're starting with our hydrogen ion concentration is 1.8 times 10 to the negative 5th. Now we have 100 milliliters of this, so we need to find out how many moles. Remember the definition of molarity, 1.8 times 10 to the negative 5, means that we have 1.8 times 10 to the negative 5 moles per liter. So when we multiply it by liters, what we're left with is the number of moles of hydrogen ions that we have. Now when we add in our 1 milliliter of 0.1 molar sodium hydroxide, which we calculated in B to be 1 times 10 to the negative 4 moles of OH. What we have here when we compare these two amounts is we're going to have an excess of hydroxide ion. So what I'm doing is I'm taking this value, which is 1 times 10 to the negative 4, and I'm going to subtract this value. So if I add these zeros in order to subtract, you can see my OH is much greater than my H. So I'm going to have an excess OH, and that excess OH is 9.8 times 10 to the negative 5 moles of OH left. That neutralizes all of the acid and leaves us with an excess of hydroxide ion. So now I need to find the concentration of my hydroxide ion. I have my moles. I need to divide it by the volume, the total volume, which in this case is 101 milliliters or 0.101 liters. So in the calculator, it's 9.7 times 10 to the negative 4, capital M, molar. Now the question asked for the pH. I'm going to find the pOH because this value is still in my calculator. So the pOH is equal to 3.0, and I'm going to give it one more digit, 3.01. So the pH is going to be 14 minus this value. The pH is 10.99 is what it looks like. Now when you have a buffer, your buffer is not infinite. Your buffer has a particular capacity, and that capacity is related to how much of the acid and the conjugate base are actually in the solution. You can also choose suitable buffers based on the pHs that you're looking to equilibrate towards. So a good buffer mixture should have about equal concentrations of its components, both of its components. Now when they say both of its components, you're looking for the weak acid and its conjugate base, or the weak base and its conjugate acid. You would also like to have a weak acid and its salt if you're looking to buffer something below 7, a pH of 7. If you're looking to buffer something at a pH greater than 7, you would prefer a weak base and its salt. Now, when you have a buffer, you can use what's called the Henderson-Hasselbalch equation. The Henderson-Hasselbalch equation is only useful when you can simplify the expression. So when your concentrations are going to be greater than 1,000-fold difference from your Ka. Same rule, but here with this equation, we have an easier way to calculate the pH of a buffer solution. And the Henderson-Hasselbalch equation is right here. pH equals pKa plus the log of the concentration of the conjugate base over the weak acid. So there's a little bit of background with the Henderson-Hasselbalch equation, but we'll actually use it in the exercises on the next page.